Hello, and a very warm welcome to this webinar from Windpower Monthly, brought to you in partnership with Enertis Applus. I'm Catherine Early from Windpower Monthly. Today we'll be talking about potential reasons why so many wind projects fall short of their pre-construction energy forecasts, and what developers, engineers and investors can do to close that gap. To discuss these topics and their implications, I'm joined by three great speakers. Nicholas, please could you introduce yourself? Just say a bit about you and your role.
Yes, thanks, Catherine. Good morning, y'all. Thanks for joining this morning. My name is Nicholas Capaldo. I'm the Director of Wind, Energy, and Advisory Services here at Enertis in North America. And yeah, happy to be here to discuss with you guys some insights that we found in our work across the US. So thanks very much.
Great. And Daniel, could you do the same, please?
Yeah, sure. Thank you. Yeah, I'm Daniel Ortiz. I'm the actual director of Wind Resource Department at Enertis Barlovento Applus. Been working the wind energy sector as wind consultant for the last 20 years. Also, I'm very happy to be here to presenting our methodology and results.
Great, thanks. And finally, Eduardo, could you please tell us a bit about yourself?
Yeah, sure. Hi, everyone. Very glad to be here. My name is Eduardo Morales. I'm a wind resource engineer at Barlovento Applus. I've been conducting pre-con and operational assessments for wind farms all over the world since a few years back. And yeah, very excited to be here and discuss a lot of matters that I'm sure concerns a lot of people around here.
Great, thanks. And before we launch into our discussion, we have a couple of polls running just below the video screen. Please do take part in these and I'll announce the key findings as we move through the webinar. They're asking you, the first poll is, how confident are you in the accuracy of your current pre-construction yield assessments? So the answers vary from very confident, deviations are minimal and predictable, mostly confident, occasional deviations but within acceptable limits, somewhat confident, results vary and require close monitoring, not very confident, frequent or significant yield gaps, or not applicable. I don't work directly on yield assessments. And we'd also like to know if you could improve one aspect of the yield forecasting process today, what would it be? That's better communication and alignment between the team and the consultant, or maybe more reliable and accessible measurement campaign and data collection. Perhaps it's clearer industry standards and guidelines, or greater investment in measurement and forecasting technology. Maybe you feel it would be enhanced training and skills development, or faster feedback loops from operational data. We'll also be taking audience questions today, so please post your questions for our speakers at any point in the comment box below the video player, and we'll get to as many as we can towards the end of the discussion. If you'd like a particular person to answer your questions, please do include their name. I'm now going to hand over to the Enertis Applus team, who are going to give us a presentation.
Great, thanks very much, Catherine. So I'll jump into the presentation here. Thanks again, y'all, for joining us today. So to hopefully jumpstart some good discussion and some Q&A, we've prepared a presentation here to share some of our results and insights from some work in the energy yield assessment space in the US that we've done, and a couple of case studies that we've prepared. First, I'll start by sort of a little bit of background on the company. So Enertis is a Spanish-based company headquartered in Spain, with several regional offices globally across the Americas, including 3 offices in the US. Enertis, we've been in the US for about 14 years, and in 2020, we were acquired by Applus, a large global testing and inspection company. And then subsequently in 2023, Applus acquired Barlovento, a Spanish-based wind energy and advisory company, bringing 25 plus years of expertise in the wind energy space. And so by virtue of acquisition, Enertis and Barlovento became sister companies, and we've been partnering seamlessly and happily ever since to deliver, our suite of wind energy and advisory services in various regions globally, including in the US. Via Barlovento, we're also members of some of the main global governing bodies such as MESNET and the IEC. We have team members who sit on various boards and focus groups within these organizations, to be kind of on the cutting edge of process and standard, development and improvement in the wind industry. So that's a bit about us here today. Sort of the premise of the discussion today is to assess why we often see, deviations from in the actual, wind energy production at projects versus what was estimated at the pre-con stage. So we're going to look at 3 different projects in the US and what the main causes were in any deviations seen across, their various wind resource and energy production processes, and discuss, what the main causes, that stand in this gap are, and, how we could have or can, help close the gap, get better at these estimates to ultimately improve pre-con energy yield estimates going forward. So with that, I will pass it off to my colleague Danielle to further unpack the discussion by starting to discuss briefly some of our processes on the pre-con and operational side of things. So Danielle, take it away.
Okay, thank you, Nicholas. Okay, so yeah, let's have a look at our pre-construction energy yield assessment. So here you can see a picture of our pre-con assessment process. Our methodology follows MESNET and IC standards. We also perform periodic proficiency tests, which is carried out within MESNET site assessment expert group to ensure the consistency between our methodologies and our results. I would like just to remark here that even following the best practice energy yield assessment, those methodologies are based on assumption and model limitation, and therefore the results obtained are subject to uncertainty that might lead to gaps between forecast energy production and real energy production. We will show some examples later. So I'm just gonna explain more in more detail some parts of the methodology and the assessment. So in the data measurement part, first of all, the METMES and later data and shall be compliant with both IC and MESNET standards. We initially perform a filter and correction process to eliminate erroneous data and ensure high recovery rates. This process is necessary to ensure the data that we are using is accurate and reliable. And once we have analyzed all data we have measured on site, we perform a long-term extrapolation. So we know that the wind typically has significant internal variability. So the measurement period might not be representative of the average long-term conditions. So how do we estimate the wind resource that will be available during a project's lifetime? What to do is to apply an hypothesis that assumes that the main characteristics of wind during a sufficiently long period in time in the past, let's say 20, 30 years, will be similar to those characteristics that might be present throughout the lifetime of a wind farm. We use different methodologies for estimating long term. You can find some examples here. All of them are well described in the MESNET guideline, so you can have a look later if you want more details. And once we have this long-term extrapolation being performed, we use this data as an input in the wind farm model for estimating the gross energy yield output. We also use a power curve adjust to site-specific air density inputted to the model. And regarding flow models, we use different models depending on site characteristics. So from linear models that are commonly used in non-complex terrain to CFD models that are more suitable in complex terrain and non-neutral atmospheric stability situation. Then we include the wake losses in the estimation. So depending the site and flow characteristics, we can use different wake models from Park 2, eddy viscosity, turbo park, etc. And we also consider the blockage and large wind farm effects in the calculation. Also, the assessment of wake losses needs to include the impact of neighboring wind farms and future wind farms. After that, we calculate and estimate the technical operational losses, and we apply to gross energy yield to calculate the net energy yield of the wind farm. Typically, we include the wind turbine availability, BOP availability, non-compliance, site-specific power curve, dirt and blade degradation, high low temperature re-rating, wind sectors management, electrical losses, recruitment, etc. So losses, all categories are included also in investment guideline, so are well described in the standard. Okay, so now let's move to on the operational yield assessment process. Here you can see also an overall summary of the methodology. Our methodology is based on SCADA data analysis. We get inputs from wind turbine SCADA data, energy production at wind farm substations, alarm logbook, operation and maintenance reports, operational KPIs, availabilities, curtailments, etc. We are going to explain a little bit more about SCADA data analysis. So it consists on data filtering, reference period selections, alarm review, wind data analysis, and historical operation and maintenance activity review. So the main objective here, you can see in the picture, is to identify and filter anomalous periods of operation due to shutdowns, limited power, curtailments, erroneous data, in order to obtain a mean power output at each wind speed bin per wind turbine. Then technical availability is analyzed in detail with different causes of unavailability being identified, classified, and counted. And just to remark here, important to note that the power performance of each wind turbine are implicit in the energy results we get. So in order to determine the actual performance of a wind turbine, a power curve test must be first carried out. Alternatively, we can perform a nacelle anemometer calibration using a nacelle or ground lighter. Okay, so once we have this power curve for each wind turbine filtered, we establish relationship between production data and long-term wind resource data to get the P50 long-term gross energy production at each wind turbine. And then also we assessed the technical operational losses with highly detailed and applying specific losses scenarios for environmental losses, losses due to operational strategies, wind sector management, noise curtailment, avian losses, recruitment, etc. Important to remark here is that the accuracy of technical operational losses, it highly depends on the quality of the available information. So we really depend on what information we have available for estimating that losses. So applying the losses to the P50 gross energy yield, we get the long-term net P50 deviation analysis with the pre-con assessment and a better understanding of the environmental site condition impact. Okay, so yeah, give the floor to Nick. Oh, Nick, I think you're mute.
Oh, sorry. Thanks. Sorry about that. Thanks, Danielle. Hopefully that gives an overview to you guys of the general processes that we follow, both on the pre-con and on the operational assessment side. So here we can see a map of the country showing 3 projects that we have taken into account in the case studies that we'll present here today. As you can see, they vary significantly both in region as well as in size. We've got Wind Farm 1 in the southwest, which is the largest of the 3. And then we've got Wind Farm 2 up in the northeast, which is the smallest of the 3. And then we've got Wind Farm 3 up in the sort of north center or the sort of upper Midwest. That's sort of in between in terms of size of the projects. So here's an overview of what we did, the analysis that we took generally for the case studies, and the different things that we focused on. For Wind Farm 1 and 2, Enertis Barlovento did do both a pre-con energy assessment and an operational energy assessment. For Wind Farm 1, given the relative complexity of the site, we have focused our sort of assessment or case study around the wind flow model specifically. So we modeled wind farm 1 using 3 different wind flow models, a linear model, a CFD model, and a mesoscale model, to show how the impact or the choice of the wind flow model can impact the results. And then we've also noticed a few interesting and above what would have been expected or not necessarily known technical and operational losses at wind farm 1, which we'll discuss further as well. Wind farm 2, the smallest project up in the Northeast, we did more of a standard, operational or validation assessment for this project. And then wind farm 3, we did not do a pre-con assessment. We did an operational energy assessment, and we've looked at the results from 2 separate pre-con assessments done by other consultants to kind of show some potential deviations and some reasons of why they might have existed as well. So with that, I will now pass it off to my other colleague, Eduardo, to get into the results of our studies. Eduardo, take it away.
Yeah, sure. Thanks, Nicolas, for the introduction. Well, for the first case study, we have this wind farm located at the southwestern area in the US. For this exercise, we wanted to highlight 2 main aspects that we consider crucial for our pre-con wind resource assessments. The first one being how much impact can cause the selection of wind flow modeling, as Nicolas had already explained, and also from which estimations of wind conditions at each turbine site are derived. And the second main aspect being how much deviation we could get when there is missing information on future operation or conditions of a wind farm. So yeah, let's dive into it. Going back to the first aspect, and as you may see in your screen at the top of this graph, we are seeing the EPE from the operational assessment, which will be your baseline, because it is these operational assessments are made from actual production data. In solid blue, we've got our net energy production, and alongside it, a proportion of the energy lost due to technical and operational aspects, which for this case, it was a higher than usual value of 17% from the total gross energy, which is the sum of both sections of the bar. And then a straight line color in black goes all the way down in the graph in order to compare all of the other cases in the graph. For the other bars, we have got an EPE made with 3 different types of model. From top to bottom, we have a CFD model, a linear model, which is kind of the standard of the industry, and then a mesoscale model. All of them have been treated independently, and same inputs have been considered for each of them. So firstly, paying attention to the far right of the image, we have this strip line, which compares gross energy values estimated with each model. And here is worth noting that these gross energy values have already implicit results from long-term conditions, wake modeling, and also power curve performance, which for the record, we didn't have access to an actual power curve test made in the wind farm. So this loss has been calculated considering an internal estimation of performance given actual MetMass data and the design values from the generic power curve provided by the manufacturer. So yeah, going back to the graph, we are seeing that it is pretty clear that the CFD model performs much better than the other 2 cases, having a 1% deviation in gross versus a 2.9 and a 4.7%, and this latest one being quite alarming for the sake of the exercise. And what this part of the graph tells us is that that it is better described by the CFD model by a significant amount. And this shall not always be the case for all wind farms. It greatly depends on site conditions and how well we as consultants, of course, based on our experience, can how much how much of from our experience we could use to select the best type of wind modeling. For example, a site located near the shore could take another kind of model that better represents the major scale phenomenon that could impact on the microenvironment of the site. But for this case specifically, a CFD model performs better. With that being said, we think that it is crucial for us to get this part of the assessments right and select the best type of model. And the second main aspect that I'm sure has already grabbed your attention, it is the comparison of with the net energy production. And for this specific case, it was quite an alarming deviation that we've got, but it has its reasons. As you may see around the middle of the image, we've got deviation values that ranges between 2.9 and almost to 15% for each case that we have studied. And this is due to an underestimation of TNO losses represented in the orange and brown sections of the bars. If we have had, if we had had this information that was not available at the moment of performing the wind resource assessment, we could have get other deviation values. Of course, estimating that these technical and operational losses that we have no info could have been estimated correctly. These deviations could have been of 2.2% and almost to 6%. And just for the record, this is something that also occurs once we analyze the original pre-con assessment made by an external consultant, which yield a 6.0% once TNO losses were applied, and even though they use a CFD model. So yeah, in this other graph, we are comparing the TNO losses estimated at both the operational assessment and the pre-con stage. As I was telling you, the main cause of underestimation came from that concept of right here, which is environmental losses with a 4.7% deviation that we got. Under this category, a lot of aspects could be taken into account. Call it extreme weather conditions, wind turbine noise propagation, and as happened with this particular scenario, with this particular case, some avian mortality mitigation strategies. After a certain time period, they decided to install a bird detection system called Identiflight, which dictates the shutdowns of wind turbines when there is presence of certain species flying nearby the site. So yeah, sometimes these kind of environmental conditions are simply not addressed or even identified before the commissioning of our wind projects, and then subsequent strategies shall be applied once the operation has taken off. And this evidently affects the overall performance of our wind farms compared to what has been estimated priorly. And of course, it puts red numbers on the production goals of our project in a constant basis. So from this part of the presentation, we cannot stress enough the importance of having addressed all of the possible scenarios and conditions that could affect the operation of our wind farms prior to performing a proper wind resource assessment. So yeah, going on with the second validation case study. This one follows the story of a not so large wind farm located in the northeastern part of the US. For this case, we wanted to follow a more traditional way of assessing a wind farm. We wanted to follow a more traditional way of assessing a wind farm, following standard methodologies and the best practices in the industry. We've selected the best wind flow model that we thought could better represent the complex nature of the site. And also here, it is worth noting that we've had access to two remote sensing devices, a sonar and a LiDAR, which were quite useful for vertical and horizontal extrapolation stages of the assessment. Here I'd like to highlight that the usefulness of having these kinds of instruments to measurement campaigns in order to get much more data from the site, and at the same time reducing cost by not needing another couple of metmasts installed at the site. So as can be seen in this picture, both the gross and the net energy deviation went quite near to the real value taken from the baseline, which is the internal operational assessment, with a 1.1% deviation in the gross values and an overall underestimation of 0.6% once TNO losses were applied, which accounted for 7.0% versus a 5.5% from the baseline. And the main cause of deviation in TNO losses for this case were various, but especially in the electrical losses category, which we have overestimated them by 1.7%, which, given the small size of the project, is kind of tricky to assess them, and even more when there are not a specific site-specific studies performed yet. And yeah, last but not least, the third case study, where a wind farm located at the north part of the country was analyzed. Unfortunately, as Nicolas has already said, for this particular scenario, we didn't have access to actual wind data at the site. So we've taken the liberty of analyzing the results from original pre-con assessments conducted by external consultants prior to the commissioning of the wind farm. However, we've performed the OA in order to compare them. So similar to the last two, at the top we've got our baseline and above the EPE from the other two studies, with the respective net and gross energy comparisons and the corresponding energy loss due to TNO aspects. And here we can highlight a common phenomenon that it is very well documented in the industry, in various technical notes and papers that have already been discussed and really worked on. And it is the compensation of a bias by overestimating not only the gross energy production, but also the TNO losses, in which yield a closer to zero deviation, even though both estimations are over-predicted. To make it clearer, here we have a 7.8% and a 9.5% gross deviation, but once TNO losses are applied, this gap reduces to 6.0% and a 6.1% net deviation. For these particular cases, it didn't close the gap too much, but a lot of authors and technical experts have published studies stating that this is a very common situation in the US market since 20 years ago. And it not only affects the overall EPE of our projects, but also the uncertainties estimations, which at the same time lower our P75 and P90 values, which are quite follow for financial matters. And finally, in this graph, we can see that the main causes of this overestimation were due to BOP and wind turbine availability, and also a little bit coming from the electrical and extreme weather conditions. So yeah, just pass it on to Nick in order to wrap everything up.
All right, thanks, Eduardo. So a few points here to sort of summarize and close on. This, as Eduardo mentioned, the wind flow modeling approach and the selection of the correct wind flow model is so important. We've seen cases too where even though the numerical validation assessment that we might perform prior to selecting the model might suggest that a mesoscale model could work at the site. If the site even has moderately complex terrain, we sometimes see that the CFD model still performs better, and so we would recommend conservative approach here and using a CFD model even at moderately complex sites. And as we saw in the case of Wind Farm 1, the case study showed here today that Wind Farm 1, our CFD modeling approach for Wind Farm 1 yielded a more conservative energy yield estimate, which also ended up being closer to the actual production at the wind farm. For Wind Farm 1, as we saw with the original pre-con UA, as Eduardo mentioned, the original assessment, which was done using a CFD model, was considerably higher than our estimate using the CFD model, which was interesting. And when we looked into it a little further, we found it was attributable to a higher wind speed prediction predicted by that other consultant at the pre-con stage. And it ended up in a pretty significant overestimation on their part. And our value was, a little closer to the actual production at the project. And both consultants, as Eduardo stressed, and yes, we can't stress enough, both cases for the pre-con assessment did not include an avian loss, which often there's maybe not enough definite information at the pre-con stage to include such a loss. But this is where we recommend really having a good understanding of this. Often at projects, there is some other understanding, the project knows the kind of, species that will be present in the area. Often they have an understanding of it. And so with the help of a consultant, I think, the developer can take some maybe not too difficult or time consuming steps at that stage to sort of flesh that out a bit and go, okay, well, what does it mean if we have these species and, given other factors such as take permits or, different factors that play into it, how can we come up with an estimation of what might be needed for mitigation strategies so that a proper TNO loss for, avian mitigation strategies, for instance, can be played into the pre-con energy assessment rather than be something that is caught after the fact. TNO losses as a whole is another area that, sensitivity cases can be run, I think, and you can perform different calculations from your gross to net calculation to get an idea as well, running some sensitivities in the model. We know financial models often include sensitivities around, grid curtailment or even availability, provide, different higher haircuts for availability in the financial model that are, captured in the model separately from the energy yield assessment, but it also can be a good idea to run sensitivity scenarios in that gross to net calculation as well to assess different possibilities at your project. So us as consultants, we can help developers, and investors basically understand the potential causes and effects of energy production deviations so that they can financially model accordingly and reduce risk. So that's the goal here. So with that, I believe we'll get to some discussion and hopefully some questions.
Great. Thanks, Nick. Thanks so much for that. It was great to have a pretty technical subject explained so clearly there. So first of all, let's have a look at what our polls found. The first question was, how confident are you in the accuracy of your pre-construction yield assessments? So interestingly here, no one is very confident. So shows that this is a subject of interest to a lot of people. But 54% of people feel somewhat confident that their results vary and require close monitoring. So yeah, and the next most popular one was mostly confident. 23% thought that they have occasional deviations, but within acceptable limits. And then on the second question, if you could improve one aspect of the yield forecasting process today, what would it be? Doesn't seem to be a training and skills issue. No one thought that was the way forward or for what's needed. But clearer industry standards and guidelines, 33% of you thought that would be the best thing. And then 25% thought more reliable and accessible measurement campaign and data collection. And then not far behind that was 17% greater investment in measurement and forecasting technology or faster feedback loops from that data. So yeah, over to Nick there to see what do you think of those results?
Interesting. Yeah, that's so I guess there's a little bit of, unconfidence in the yield assessments, which is not that surprising, I guess. So, what was indicated in the second poll question is, I think that the top answers there are things that us consultants can help with, like making sure that you have, a bankable and robust measurement campaign, for instance. And remote sensing devices, of course, are becoming more widely used. And helping you understand the industry guidelines as well, I think is another area where consultants like us can help with as well. Danny, do you have anything to add there?
I think I agree with you. Yeah, seems that
Yeah.
there is some space to improvement in the energy yield assessment. Hopefully, I think that there are also a significant percentage of mostly confident people, which is quite good. I think that all consultants are working really hard to improve the confidence in our results in energy yield. So let's hope that probably if we ask again this question in the future, we can reach a higher percentage.
Yeah.
Okay, great. We've got some time now for questions. Let's just get started with a few from me. Nicholas, maybe you could explain why is it so important to get these wind energy forecasts right from the start? What's at stake in terms of project performance, financing, and long-term asset value?
Yeah, well, of course, I guess maybe the more obvious answer is the financial performance of a project. Obviously, the energy assessment feeds directly into the revenue build for the project. And so getting that right will have a direct impact on the revenue generated, of course, from the project. And then it can also, impact LDs that might be payable under the offtake agreement. So, the energy assessment for a couple of reasons there financially is important, of course. And the uncertainties come into play. Of course, many projects we see financed on the more conservative P values, like the P90 or P95 value might be used for financing. So where, of course, if we can bring the uncertainties down and keep the uncertainties as low as possible, there's less of a spread there across the p-value spectrum, bringing the P90, P95 sort of in closer to the P50. And so, of course, uncertainties, can be reduced by a robust and bankable measurement campaign, and then, sound industry standard practices in wind resource assessment and energy modeling. I guess I'll add to that too, maybe given the current industry challenges that we're seeing, like tariffs, higher material and equipment costs, and possible step downs in the tax credits. There's a lot of other factors going into the financial models that carry increasing levels of uncertainty these days. And so, higher CapEx, with uncertainty around tariffs and higher material costs and equipment costs, means that getting the revenue part of the financial model, as close as we can and with as low uncertainty as possible is becoming increasingly important given the other sort of factors with more uncertainty these days in the market.
Okay, great, thanks. And next, I was wondering what proactive steps developers, owners, and investors can take to close the yield gap, and how can smaller developers or projects with limited budgets still effectively reduce measurement uncertainty without significant investment?
Yeah. So as kind of mentioned there, we can expand on it a bit, like ensuring the quality of your measurement campaign is key, following the guidelines from ESNet for measurement hub height or measurement, sorry, in relation to hub height and the number of years, the period of your measurement campaign, of course, and then the use of remote sensing devices can, of course, improve your ability to understand the wind resource across the site and also to hub height, so that horizontal and vertical extrapolation. And then, as we've mentioned before, we can't stress enough the importance of understanding the environment around and the species that might be there, and knowing what's going on at your site and what should be accounted for in the pre-con assessment. So us as consultants can, of course, help in these areas to make sure we get the pre-con assessment right. Smaller developers or lower budgets, use of remote sensing devices to either replace additional met masts, I can say. Maybe Danny, you can help expand on the use of remote sensing devices and also maybe talk a bit about power curve testing during the operational stages?
Yeah, sure. Yes, as you mentioned, remote sensing devices is a good option to try to reduce the uncertainty of the overall assessment with control budget. So the idea is to measure all across the wind site using one or two remote sensing devices, depending on the size of the wind farm. But at the end, you can cover more area. You can reduce the impact of wind modeling the uncertainty using this remote sensing device. Also, you can reduce the impact of vertical extrapolation using that device, so you can close the gap in that sense. So we have seen in the presentation that in that case in which we had this remote sensing device, the deviation we had was lower. Also, we show the impact of the wind modeling, so it's also interesting to assess the appropriate to use the most appropriate flow model for assessing the energy yield. And also it's quite important, at least from our side, from our view, to perform a power curve test after or before the wind farm construction, to at least guarantee in your turbine supply agreement to assess with more warranties the operational assessment after the wind farm is operating.
Great. And Nicholas, I was wondering what makes the challenge of energy yield forecasting particularly pressing in the US wind market today?
Yeah. I think I already kind of touched on it, but the current market challenges around tariffs and material costs and stuff, putting increased pressure on the financials, increased uncertainty on the financials, makes it so that I think there's more pressure on us to get this step of it right, and to not optimistically predict energy or over predict essentially. So and then to reduce uncertainty so that those more conservative p values that are often used for financing are sort of closer in a narrower range. So kind of quality met campaign and the correct modeling approach, strong understanding of all T&O losses, are all ways that we can help our partners, the developers, get it right at the pre-con stage. Also, repowering of vintage wind assets is becoming increasingly important in industry, and how the industry will move forward, I think, is repowering older projects. And so understanding how production will be increased through repowering is also important. And then I guess maybe I'd add to that too, with the uncertainty around potential step downs of the tax credits. It's there are certain repowering options that are maybe lower cost options to improve reliability of some other components. So a less costly repower one that might not qualify for the 80/20 rule, but that can offer significant reliability improvements, increase energy production, and also maybe lower OpEx there as well. Maybe Eduardo, do you want to expand on some more technical aspects to this question?
Yeah, sure. Just to add, as you said, a more technical point of view of these kind of challenges. As you also pointed, the wind turbine fleet at the US is kind of maturing. There is a large portion of wind turbines all across the country that are well over 10 years old. And these kind of wind farms usually present or tend to present problems such as power curve performance degradation, mechanical components fatigue, variability in maintenance programs, and all of these factors, of course, compromise the differences that could appear with the initial EYAs in the long term. Also related to this, strategical decisions such as whether to replace or upgrade wind turbines with newer and more efficient technologies also depends heavily on the accuracy of EYAs at the beginning of the lifetime projects. And also, I would like to add that we cannot deny that climate change is also is not only producing an increase in interannual variability of the wind regimens and any change in its patterns, but also it introduces the possibility of more and more unpredictable extreme weather events that translate into larger periods of downtimes, and also that compromises that the BOP and maintains programs for our project. So I think that all of this makes an impact on the accuracy of initial energy yields assessments in the long term.
Great, thanks. And Daniel, I was wondering if you could tell us a bit about best practices that are emerging to improve forecasting accuracy and reduce uncertainty. Are there specific advances in wind measurement, data analysis, or modeling tools that stand out, do you think?
Yes, sure. Yeah, well, I would like to insist that still the most effective way to reduce the uncertainty in the pre-con assessment is to improve the measurement campaign. So yeah, with good quality in the measurement campaign, more years of data measured on site, the use of these remote sensing devices to measure not only in more areas, but also measure at higher heights, and it can also lead you to measure additional parameters like wind bear, vertical wind shear, upflow that might impact on the power curve and the performance of the wind turbine. So I think that this is probably the best way to reduce the uncertainty. Also, once you have all these variables measured, it's probably more visible to ask the wind turbine factor for a site-specific power curve, because you can reduce more the gap between the future real energy production and the forecasting energy production in your pre-con assessment. Also, there has been a lot of improvements in wind modeling. So years ago we only had the linear model. Now the CFD models are like standard models in the wind industry. Now we are coming to use these LEIS models. We have these open source wind flow models that anyone can use and can apply. Also in wake estimations, especially for large wind farm or long wind turbulence intensity sites, we have new wake models like Turbo Park and other models. And I think the industry and academy have also put many effort for better understanding on blockage effects and better estimation on blockage effects. And of course, I think also following the last version of the guidelines like MESNET or IC standards, like new DAS 15 standard, I think that could lead to reduce this gap. So the standardization groups are continuously working on improving the methodologies and getting more accuracy results.
Great, thanks. And Eduardo, how can these deviations be diagnosed and traced back to their root causes once a project is operational? What are the limits of what pre-construction modeling can predict?
There are a few aspects that could be considered for diagnosing deviations during the operation of our wind farms. The first one that we can advise or developers is the usage of wind data from the METMAS installed at the very project in order to have accountability of interannual variability of the wind regimens, and also to trace back exactly what are the differences from the expected wind speeds predicted in the initial EYAs. And also that something that we could advise every developer is to perform deeper analysis on operational data or operational matters of the wind farm with events log files or overall SCADA data that it is very well documented on a constant basis in order to estimate the energy that it is lost at each shutdown of some wind turbine or at each limitation of power in order to also categorize them in a more rapid way and attend the causes of those downtimes. And about your second questions related to limitations of pre-con assessments, apart from what we have already discussed, one aspect or limitation that comes to mind is the long-term estimations that are quite hard to assure their consistency in a future scenario. And I mean, it is true that 20 years of data, or even 25 or 30 years of reference data from pre-analysis time series, or even another reliable data source, are a good indicator of how the wind is going to look in the future. However, it is very hard to estimate exactly the impact of other external factors, as I mentioned. For example, climate change could produce in the behavior of the wind farm in the long term, in the actual long term. And another one that comes to mind is the affection due to future developments that could take place near the site that have not been considered in the assessment, such as building constructions, changes in vegetation around the turbines that could represent obstacles in the wind flow nearby the turbines, and of course the implementation of wind farms that could that haven't been considered in the pre-con assessments, since maybe developers can have a window to the future of 2 or 3 years from the commissioning of the wind farm, but maybe they don't have any information on even more future projects in a 5 or 10 years window. So those kind of developments could introduce wakes and turbulence to our projects, affecting not only the overall EPE, but also causing fatigue on mechanical components and then the balance of plant itself.
Okay, thanks. And finally, I mean, Eduardo, maybe you could just tell us a bit about where the biggest discrepancies between forecasted and actual energy output tend to come from.
Yeah, sure. Well, as kind of said in the presentation, TNO losses is one of them. Wind flow modeling also, as we have already explained, also as I have already mentioned, is the long-term wind conditions scenarios that we can also find the big differences around there, since we are estimating the future from historical data. And another few aspects that, of course, the industry is working towards being more precise and accurate in order to reduce those gaps, especially wakes estimation, and not only from the wind farm itself, but also from neighboring wind farms, which is a quite hot topic nowadays in the industry. The interaction between neighboring wind farms that are around 50 or even 100 kilometers apart, depending on if it's offshore or onshore. It is something that we are trying to address in a more efficient way, and the wakes stage itself is kind of one of the main aspects that also is very hard to assess prior to the operation of the wind farm.
Great, thanks, Eduardo. And now we have a few more minutes for audience questions. We have quite a few of those coming in, so thanks for that. The first one is about the modelling. Was high-resolution mesoscale modelling used for the complex terrain?
For this particular case, especially in the first validation case study, we try to analyze independently all of those three wind flow modelings in order to assess exactly how much they behave and estimate the horizontal extrapolation at the site. But it is true that it is also very common to mix up some of the wind flow modelings. For example, we can mix a CFD model and put a high resolution mesoscale input in order to assess both parts or both patterns that each wind flow modeling describes the best. So yeah, for this case, we didn't make exactly that. We try to independently study each wind flow model, but of course we can mix up wind flow modelings in order to assess in the best way the complex nature of each site.
Okay, thanks. We've got a few questions about the case study wind farms. Could you explain again how you get the gross value from the operational data? SCADA data will include wake losses and turbine performance losses.
Yeah, sure. The SCADA data, as it has been stated, it includes wake losses. The other ones, the turbine performance losses, are also implied. And they are implicit, and it is kind of the standard methodology to not try to exclude them, since it's a more difficult way to extract each cause of loss. But yeah, it is they are always implicit, and then in the long term in the long term estimation we are also using those values with that in mind, that those wake losses and the turbine performance losses are already implied in that. We don't discretize them from the from the energy value. In order to make that, we should get more data from the SCADA data. For this particular case, we only get the basic input. We only got wind speed and power 10 minutes data. But in order to assess wake losses, for example, we also need values of pitch angle. We also need direction from the wind, maybe the usage of wind data from MetMast, that it is not perturbed by but the wakes itself from the rotors. So yeah, it is necessary a lot of other inputs, and that for this particular case we didn't have access to. So we decided to include the energy values as they were, with those implicit loss in mind.
Just to add something, sorry. Yeah, also we have no power performance test available for this analysis. So in case that we had a previous power performance test, then we can extract the actual performance of the wind turbines and compare with the theoretical one or the one that we obtain in the power performance test. But this is not the case in this exercise. Also, if you haven't, but you want to extract this power performance or the wake effect, you can perform this anemometer calibration using nasal laser or ground laser measurements. Also, you have more information, as Eduardo said, about the SCADA data, more variables available. You can somehow extract the wake effect, but it was not available in that case.
Okay, great. And we're running a bit short of time here. I believe the guys are going to get back to people individually if we run out of time not going to have time to get through all the questions. So I'll just ask one more here. What improved methods of accurately modeling forestry are being developed? Bit of a different topic there.
Yeah. Well, there's have been there are a lot of papers that have been published about modeling and forestry. So yeah, we are aware that all the wind flow models are making efforts to include the forestry modeling and to try to include the forest, especially turbulent effects on the wind turbine. And it's true that yeah, it's not a common approach on that, because each model has its own solution for dealing with that forestry. So there are some models that just add some momentum structure to the models. There are other modeling that deals with displacement height, which is more or less what is described in the IC-15. But yeah, it's true that there are not common approach on that.
Okay, great, thanks. I'm afraid that's all we've got time for today. I hope you found the discussion useful. It'll be available on demand once the session is over. Many thanks to our speakers, Nicholas, Daniel, and Eduardo, for your insights, and to everyone else who's joined us today. I'd also like to thank Enertis Applus for partnering with us. Thanks for watching, and hope you join again soon.